So now we're on to our second type of condensation, and this is condensation that is a bit above the ground. It's still near the ground, and it involves fogs, both cooling fogs and evaporative fogs. And both of those types of fogs fit into our discussion of how to get to condensation. We were talking about getting to condensation by adding vapor to our parcel of air, or by reducing the temperature of that parcel of air. Well, the cooling fogs seem to go right along with reducing temperature, and we'll talk about those first. Then we'll talk about adding vapor, and that makes sense in evaporative fogs. We are evaporating into that parcel. Let's look at the cooling fogs first. Again, this is something that's probably going to happen overnight, with the condensation happening toward the morning as the atmosphere really cools down and meets the dew point. In other words, you have air, not objects this time. You have a temperature minimum for your air parcel that has been dropping overnight. It doesn't have a lot of the radiant energy left from the ground. So the temperature is dropping overnight, it meets the dew point, it goes below the dew point, and condensation is starting in here for the fog. There are three different types of cooling fogs that generally show up overnight. There's a radiation valley fog, an advection fog, and an upslope fog. Let's look into both of them, or all of them, I should say. The radiation fogs are definitely associated with overnight fogs. They are produced by the Earth's radiational cooling from the ground. The ground emits infrared overnight, so the soil gets cooler. Over the course of the night, the entire valley may get cooler. The hillsides will get warmer because they are getting the infrared at a higher altitude. So this radiates up from the soil in the valley, leaving the valley cool and leaving the hillsides warmer with the infrared radiation. When that cool valley soil meets the dew point, there will be fog there in the valley. The fog has a lid or a cap on it up on the hillsides, and the fog disappears in that area because those hillsides are warmer and they really support the vapor. They don't support the condensation. So you'll hear about a blanket of fog in the valleys, but that fog is not going to rise up through the valleys because this area along here is warmer from the infrared radiation. That's why we call it a blanket of fog, radiational fog. Here's a way you can see that from a parking lot. It's not easy to see, but it's a really neat phenomena. This is fog in here over a cool football field. That cool football field radiated energy out all night long. The soil became quite cool, met the dew point, condensed the vapor into a low fog. Here is a fog that is higher over the warm parking lot. The warm parking lot is supporting vapor and is not supporting condensation. But a little above the parking lot, that air does cool and can condense and form a fog a bit higher. So what I really want to point out to you here is the low fog over the cool field. This is a more complicated fog because we have learned about the warmer temperatures above these areas and shutting off this fog where the warmer temperatures are. In this case, it's kind of complicated by the fact that you've got a warm parking lot that's sending that fog into a very narrow strip before it disappears again in the warmer environment at a higher altitude. So this is a very thin fog in here and a very tight gradient of that temperature that could meet the dew point. In terms of advection fogs, frequently seen in San Francisco and along areas that have a very cool current. What is happening is that farther out in the Pacific, there is mild water that evaporates up. But near San Francisco, there is a very cold current, and as that vapor moves over the cold water, it chills. It can meet the saturation vapor pressure, it can meet the dew point, and condense there to form really thick fog. This is called advection fog that is driven on the wind. Ad is toward, vecto vectore is wind, toward the wind. This fog is driven over a colder water area, cools and condenses there. Let's look at where that cold water actually is. This is the San Francisco Bay Area. This is a Pacific current which forms a very cold segment right near San Francisco. We're going to learn why in chapter 7 when we talk about circulations. But for right now, except that there's a really cold current right near San Francisco, when this parcel of air that has vaporized off the warm water that's out in this area is driven in by westerly winds, it reaches the cold water and the temperature of the air cools and meets the dew point and is driven in by the westerly winds on an advection fog. They can be very deep fogs. Third type of cooling fog is an upslope fog. This forms as moist air becomes more buoyant. Remember, humid air is buoyant, and it runs up a slope where it can't run through anymore. It has to run up along a mountainside. It chills on the elevated mountainside and condenses there to form upslope fog. We frequently see this where we have the situation of humid air and a beginning of a mountain range. Look at this. On the eastern side of the Rockies, we will have upslope fog formed from the humid air from the Gulf of Mexico that is rising and hitting the eastern slope of the Rockies. So that Denver is known for its upslope fog. And in terms of the other cooling fogs, we're finding the advection fog along the California coast, but also we see advection fog in the cooler areas of the Canadian maritime coast. Because remember, that advection fog comes and is driven in across a colder water area where that vapor will condense. You can also see advection fog along the Gulf Coast. Even though there's no cold water in that area, the ground is so warm that the water is cool by comparison. So when the winds off of the Gulf of Mexico drive that vapor, that will hit an advection fog area in that area. There's also radiation fog in that area as well. But this is where we tend to see cooling fogs across the United States. When it comes to cooling fogs, of course, we have 3 different kinds. And then we have warming fogs or evaporative fogs. These are fogs that add water vapor to produce condensation. And they're warming and evaporative fog, those two things go together. Warmer temperatures produce more vapor. In this case, this is the type of fog that you might see above hot springs or above a heated pool in winter. This is a very nice warm pool. You don't have to worry about them being too cold. It's kind of like a sauna in there. And that warm water will evaporate off into this area right above the pool. But that mixes with cold air, and that vapor will super saturate that parcel of air so that it will condense very quickly. It's a thin layer of air in that mixing evaporative area that is caused by the warm air evaporating. This is Yellowstone National Park, and here we've got warm air. This is a summertime shot here. This is warm air, but the vapor is so hot from the geyser that the air in here feels cool by comparison and condenses out. So these are evaporative fogs that are forming a lot of vapor in this area that can condense in cooler air. I'll see you for the next one, which is formation of clouds in the upper or in the lower atmosphere.